Okay. So, hello, my name is Lida Michalaki, and today I will describe strange behavior that happens in a pharmacokinetics model. Specifically, this behavior was observed while studying the kinetics of a target-mediated drug disposition model, which refers to the binding of a drug to a specific receptor in order to create a drug-receptor complex, which is the active form of the drug. TMDD refers to biological drugs, such as the therapeutic monoclonal antibodies, but studying their mathematical models is not easy because we have to identify all the model parameters, and because these models are strongly non-linear and multi-scale. What will follow is the presentation of the full TMDD model and the method of analysis applied to stiff systems. Finally, I will present some of the results, focusing on the case where we have an opposing outcomes of a reaction. So this is the mechanism that describes the full TMDD model. Consisting of 5 variables and 10 reactions. For the case of the subcutaneous dose, initial quantity of the drug is administered in the depot compartment, through which it transfers in the central compartment, which is the blood plasma. From there, the drug C binds to the biological target R in order to create the complex RC, which is the effective form of the drug. Also, drug from the central compartment can transfer to and from another compartment, the tissue compartment. And regarding the biological target R, it is produced and decomposed regardless of the presence of C and RC in the system. If we consider this case as a homogeneous case, this is the mathematical model that describes the response of the system, where CD, C, and CT refer to the various forms of the drug, R refers to the biological target, and RC refers to their binding. And these are the reactions rates whose expressions are given here. Now we can see the response of the system through time. In the beginning, the only variables that have a non-zero value are of CD and R, and as CD decreases, we can see that drug is transferred in the central compartment. So C is formed. Once C is formed, it binds to the biological target R, so R reduces in order to create their binding RC. In this phase where the formation of RC is stable, the drug is active and effective. Once C is consumed, then the biological target R reaches the steady state value and the system dissolves. The steady state value of R is a result of the equilibriums for reactions 8 and 9, which are regardless of the system. So among the strange behaviors that we studied in this model, we focused on the case of the reaction for C in the central compartment. And we saw how it is affected when we played with reaction 7 rate constant, KTP. Reaction 7 consumes CT in order to produce C. So by increasing KTP, which is the reaction's rate constant, we expect lower values of CT and higher values of the product C. As we can see, when we doubled this variable, initially we saw what we expected, lower values of CT and higher values of C. However, in the long term, the behavior for C was reversed, and we see that C decreases with an intense rate. This is what I'll try to explain later on. So we had a first indication that the TMDD model that we studied is a multi-scale one. When we studied the trajectories in phase space, here we can see the projections of 5 trajectories, each one referring to a different set of initial values for C and CT. Their beginning is marked with a bigger circle, and we see their directions pointed with arrows. The smaller circles refer to equidistant temporal points, and we see that in the beginning we have a fast response of the system, which later becomes slower, and in the end all the trajectories coalesce into the CT axis. This is only a first indication that the TMDD model we studied is a multi-scale one. We can be definite by studying the time scales of the system. By time scale, we define the inverse of the eigenvalues of the system, and by time scale gap, we define the fraction of successive time scales. Here we can see a gap among the first and the second time scale. Another one exists between the third and the fourth time scale, and between the fourth and the fifth. So, as the system we study has time scale gaps, and all of the time scales are of dissipative nature, we know that this system is admissible to singular perturbation analysis. Given a multi-scale system of ODEs, it can either exhibit a wide range of eigenvalues with the fastest one being negative, or a wide range of complex eigenvalues with the imaginary part being far greater than the real. The first case, in which the TMDD model we studied belongs, is typically studied with singular perturbation analysis. However, using SPA is not easy because we have to do a suitable separation of variables to slow and fast, to write the non-dimensional system in an appropriate non-dimensional form, and to determine the small parameter epsilon. The geometric theory introduced in the 70s made this analysis much easier, because GSPA identifies the dynamical structures that develop in phase space, such as the invariant manifolds, and focuses on their dynamical properties, which is the decomposition to fast and slow into the tangent space. Now let's consider a three-dimensional ODE example and assume that one of the time scales is much faster than the rest. A slow invariant manifold is called a low-dimensional surface towards which the solution is directed because of the act of the fastest time scale, here tau 1. Once the solution approaches sufficiently close to this manifold, the fast time scale becomes exhausted. For every exhausted time scale, the dimensions of the seam reduce by 1. Along the seam, the evolution is characterized by the fastest of the slow time scales. Now, considering a point along the manifold, a new axis system is introduced consisting of the basis vectors A1, A2, and A3, where A1 points to the fast direction and A2, A3 point to the slow directions. Then, the vector field G can be fully decomposed into the directions of A2 and A3 and has a negligible contribution towards the fast direction of A1. The axis system of A1, A2, and A3 evolves in time because the fast and the slow subspaces rotate. However, the vector field G is always fully decomposed towards the slow directions of A2 and A3 and has a negligible contribution towards the fast one. Now, the theory did not provide any tools to continue with this analysis, so that was done by computational singular perturbation, which introduced the basis vectors A1, A2, and A3. And as I will show you next, these vectors are all that we need in order to reconstruct the seam and the slow model that describes the evolution along the seam. So, consider a non-linear system of ODEs, the right-hand side of which consists of k terms, each one referring to a different physical process. According to CSP, the right-hand side can be decomposed towards the end directions of the tangent space, and then we can combine the components of the fast direction and the components of the slow direction. So, after we combine the components of the fast direction and of the slow ones, we know that along the seam, the fast direction, the fast dynamics are negligible. So, Fr, which is the amplitude of the fast direction, is asymptotically small. What's left from this equation is a slow system that describes the evolution along the seam. And all we need is to describe to find these basis vectors A1, A2, and A3 that are respectively to the dimensions of the system. This is done by the two algorithmic procedures, the BR refinements that improve the accuracy of the system and approximate AS and FR, and the AR refinements that provide stability and approximate AR and FS. So once we have the basis vectors of the tangent space, we are allowed to employ some algorithmic tools that give a physical understanding of the process. So we have the CSP pointer given by this expression that points the variables that are most related with every mode. The CSP amplitude participation index, or API, that indicates the reaction, the contribution of a reaction to a CSP mode. We have the CSP eigenvalue participation index, or EPI, that indicates the contribution of a reaction to the nth eigenvalue and so to the nth time scale. And for the slow dynamics, we have the CSP importance index that indicates the contribution of a reaction to the evolution of every variable along the scene. Now we can see how CSP is applied in a specific case. Let's consider the case where the time scale gap of interest is between the third and the fourth time scale. In this case, we have 3 fast components and 2 slow. And by definition, the fast components have negligible contribution along the scene. So these are the relations that construct the scene, and this is the system of ODEs that describes the evolution along the scene. In the graph, we can see the amplitudes produced after 1 and after 2 BR refinements. And as we can see in this area, after each refinement, the amplitudes become smaller, which is what we expected. So now we know that the solution evolves in a 2-dimensional system, in a 2-dimensional scene. In this whole area, we have the ability to produce algorithmically all the diagnostics tools in order to have a physical understanding of the system. As an example, we can see a specific point of the area where m equals 3, and we have the results for the first, the second, and the third exhaustive mode. As we can see, for the first exhaustive mode, CSP pointer identified as highly pointed the variable c and secondary RC, and the CSP amplitude participation index indicates a balance between reactions 5, 6, and 7, where through CSP EPI we know that this time scale is generated by the act of reaction 5 that consumes the highly pointed species and reaction 6 that consumes the secondary pointed species. As for the second mode, the CSP pointer identified as highly pointed the variable RC and secondary C with the equilibrium that is valid between reactions 5, 6, and 10, where these reactions are responsible for the generation of the second exhaustive timescale. For the third mode, CSP pointer identified variable R as highly pointed, and CSP API indicates an equilibrium among reactions 8 and 9, with 9 being the fastest one. As for the slow dynamics, CSP importance index indicated that mostly for all the variables, reaction 7 is the one responsible for their evolution along the scene. As we can see, reaction 7 has a negative contribution for the evolution of C, which means it tends to reduce it. This is the opposite of what the mechanism indicates. And this result matches to the strange behavior that we saw in the beginning. Now we can see the response of the system with a different eye. We have this area where we have 2 exhaustive modes, and the equilibriums that are valid are between reactions 5, 6, and 8, and 5, 6, and 10 for each one of the exhaustive modes respectively. Then we have this area where we have 3 exhaustive modes, and the equilibriums are between reactions 5, 6, and 7, 5, 6, and 10, and 8 and 9 for each one of the modes respectively. What really happens is that we have a 3-dimensional scene here, and then we have an intense activity where the manifold dissolves. After that, the solution approaches to a new 2-dimensional manifold, which is in this area and is characterized by a smoother response. Now we can see the same charts and compare that to the case where we intensified reaction 7. By intensifying reaction 7, we expect higher values of C because it's the reaction's product. More C in the system available to bind is expected to reduce R. So in the first area of the 3-dimensional scene, we see that what we expected happened. We have higher values of C and lower values of R. However, in the second area, where m equals 3 and we have a 2-dimensional scene, we see that the behavior for C reversed. and C reduces more intensively. If we focus again in this area, where the manifold dissolves, we see that R reaches the steady state value with a small time delay. During this time delay, the intense activity continues for all the variables. So C lands to the next manifold of this area, having already taken a lower value. And as we saw from the dynamics of the slow system, from the algorithmic tools, in this area, the evolution of C is driven by reaction 7, which tends to reduce it. This is why we see the intense reduction from this point on. We can have a further insight of what's happening if we study reaction 7 in phase space. We can see that in the phase space of CT and C, if we take the trajectory of the initial case and study the stoichiometric vector of reaction 7, we see it tends to increase C and reduce CT as we expect. However, if we decompose this vector into a fast and a slow contribution, we see that the fast contribution tends to overproduct C. In order to compensate to this act, the slow contribution takes a direction towards reducing C. Along the seam, we saw that the only contribution that matters is the slow one. So we end up having an evolution of C towards the opposing direction that the mechanism indicates. So in this point, I want to summarize the basic parts of my work. First of all, regarding the method of analysis, CSP gives us the ability to identify the reactions that generate the fast time scales, that participate in the equilibria that generate the seam, and that drive the system along the seam. And as for the TMDD analysis, the CSP method revealed that we have a transition between fast and slow periods, where the first slow period is, in the first slow period, we have a quasi-steady state approximation for R and RC, and in the second slow period, a quasi-steady state approximation for R, RC, and C, where the process is driven mainly by reaction 7, which products C. Among the strange behaviors that we identified, we saw that by intensifying the action of the 7 reaction, we had a result that is opposite to what we expected, lower values of the product. And as I tried to show you, that is due to the landing of the trajectory in a different point along the second two-dimensional seam. That is all from me.
Thank you very much for this interesting talk. And who wants to ask questions? Sorry. Because you usually pose questions, and I think you sorry. Please give the young scientists a chance to discuss and pose some questions. Please.
It's a generic question, but to what extent identifying those quasi-equilibrium state is easy in any system, because you focus on that specific system. But if I take an arbitrary system of dynamical equation, how easy is it to have a kind of systematic procedure to identify the different time scale over which I can define quasi-stationary?
First of all, it depends on the system. The method I presented to you today is applicable only when we have timescale gaps that give us the only thing we need in order to apply CSP. Apart from that, it's easy, once applying the method, it's easy to identify the approximations valid and to see what's happening with the physical, to get a physical understanding of the model. I don't know if that's what you meant.
But identifying those gaps, how would you do it if I give you a set of nonlinear differential?
I can study the timescales that develop in the system, and by introducing the appropriate accuracy that I need, which is introduced by the timescale gap, the ratio of the timescales, I can see whether this method is applicable or not.
I have also a question, maybe to Professor Goussis. What is fast and what is slow? What's the difference between fast and slow? We had a model which was much simpler than that, with only 4 variables going on, an ecological model, and then long ago, 20 years ago, and then Professor O'Malley, who is specialist in singular perturbation theory, came and said it depends on the system and so on, and should be the factor 10 or something like that. But then we made some simulation, and it turned out it was the factor 4 or 5 times as fast and so on. And could you answer, in your special case, what's the difference between fast and slow?
You mean as a...
The epsilon.
It's produced by taking the fast one-time scale as a ratio to the next one. And if that is of appropriate epsilon,
Yeah, but what is appropriate? That's the question. When does the theory apply?
Whatever characterizes the evolution of the process, this is slow. Okay? And everything else above that is fast. Now, the nice thing, this is easy to say, okay? But the nice thing is that this algorithm gets this information for you algorithmically.
As a result of the algorithm.
It's like a black box.
Yeah.
So you input the model and you get all this information.
Is a change of parameters, the gap can become smaller, and at some point it doesn't expand easily.
No problem.
Thank you very much.